In this video, I'll be going over my first IC design project. I've always been interested in integrated circuits, but the complexity of their design process was preventing me from getting involved. However, I discovered that there are software tools that can turn HDL modules into digital IC layouts without the need to draw any of the transistors manually. Then, the only obstacle left is the high cost of fabricating an IC prototype. This is where Tiny Tapout comes into play. It's an open source project that allows anyone to purchase a portion of a large IC die to place their design there. After I learned I can get my chip fabricated and placed on a custom PCB for only $100, I knew I had to start working right away. When it comes to my project idea, I decided to make a direct digital synthesizer, which is basically a digital sine wave generator. In addition, the device would be made specifically for RF communication. This is the workflow I used to turn my idea into a real chip. I used Verilog as my HDL and simulated my design in ModelSim. Then I used the GitHub template provided by Tiny Tapout to generate the fabrication files. This is the final architecture of the device. It's an expansion of the standard DDS architecture with two programmable frequency control registers, which makes it possible to use the device as an FM or OOK transmitter. I also included a UART module for interactions with microprocessors. Here we can see how the pins of my device map to the pins of the Tiny Tapout chip. This diagram shows how my DDS can be used as an RF transmitter. It's controlled by a microprocessor, and its output is connected to a DAC. The DAC output has a DC offset, which is then removed by a low-pass filter. Finally, the output signal passes through a power amplifier and is sent to an antenna. All my previous digital design experience has been on FPGAs, and working on this project taught me a lot about the considerations that need to be taken when writing HDL for ASICs. In my project, I was able to significantly reduce the chip area by replacing flip-flops with combinational logic in the lookup table, as well as by using 16-bit wide signals instead of the typical 32-bit. In addition, I had to move all initial states of all registers into reset statements, because in ASICs, flip-flops are not initialized to known values at startup, unlike in FPGAs. Let's look at some simulation results. Here we can see the output of the DDS when using OOK modulation. Note how the sine wave is present when the RF data pin is set to 1 and absent when it's set to 0. This figure shows the output of the DDS when using FM modulation. Note how the sine wave switches between two different frequencies, depending on the value of RF data. As we can see, my device requires only 583 logic cells, occupying 35.7% of the tile. This is the final layout of my chip generated by the OpenLane tools.